Hello Year 11, this is a video for the predictions for the chemistry exam that's coming up on Monday. This video is for both combined science and for separate or triple science. Okay, on the screen now you can see the predicted content. So this is content that we feel could come up in your exam on Monday. Now, as you can see, that is a huge long list. And what I've done for this is I've combined the combined science and the triple into one video. So you can see that there are very similar predictions for combined science and for the triple separates paper. But if you are a separate pupil, triple pupil, then I would recommend that you also take a look at fuel cells. Now what I'm going to do is I'm going to do a walkthrough of some of this content. The reason why I have included so much predicted content is because there is so much that is linked in chemistry. I can't go through all of this in a short 25-minute video, so I've picked the key things that I think will come up from our predicted content list. There is a lot of things that I won't cover in this video, and I would recommend that you go away and have a look at those other things using some different resources. So let's get started. Okay, first up we have the structure of the atom. So it could be presented to us something like this, where we are given a diagram and we are asked to write some information about this. So we need to know that the middle of our atom is called the nucleus, and inside the nucleus there are two things. We have protons and we have neutrons. Neutrons do not have a charge, so as you can see here they're just coloured in black. These are neutral. But we also have our protons there, but they have a charge. They are positively charged, and these are the things that make up our nucleus. Surrounding our nucleus, we have electrons, and these exist in shells, or you could call them energy levels. We call these subatomic particles, and these subatomic particles have different charges and different masses. This table here summarises the differences in the charges and the relative mass. So our proton has a +1 relative charge and a relative mass of 1, neutron, no charge and a relative mass of 1, electron, a -1 relative charge and a relative mass of almost 0. So the majority of our atom's mass is made up of our neutrons and our protons. Electrons do have a mass, however it is so small we say it's negligible, means it's almost 0. So what does that mean then in terms of the periodic table? This is a picture of an atom, but it's of a particular atom, and this is of carbon. So if I was to go to the periodic table, which you will be given in your exam, you would look at that symbol and you can see two numbers, and we need to know what those two numbers represent. So the top number is your mass number. This tells you the number of protons and neutrons, and that's because these are the subatomic particles which actually have a mass. The bottom number tells you your atomic number. This tells you your number of protons. So instantly you can determine that there would be 6 protons in a carbon atom. Now you might be asked to work out the number of electrons and the number of neutrons using the information on the periodic table. So you need to know that electrons will always be the same as our protons if we are talking about an atom. So an ion would be different. That would be if it's got a different number of electrons, but for an atom which has no overall charge, the electron number will always be the same, and that's because you want to have the same number of positive charges as you do negative charges. Now to find the number of neutrons, you have to take your mass number and then you have to take away the atomic number from this number. So in this case, we would do 12 minus 6, which just so happens to give us the same number of 6. Okay, here's another example. Here's lithium. So instantly I'm looking at that bottom number to tell me the number of protons. The number of electrons is going to be the same because it's an atom with no overall charge. And our number of neutrons is going to be our mass number of 7 minus 3, which is our proton number, and this time it gives us 4. So that's for our lithium. Now we also need to know that our electrons are arranged in a particular pattern. So we know that lithium has 3 electrons. Here is an image on the left there of lithium's atom, and you can see the electron arrangement. Now potassium is another atom where we can see its electron arrangement. Let's look at that on the periodic table. As you can see, our bottom number here is 19, and that would mean that there are 19 electrons. So that's different to lithium. Now, the rule that you need to know for electron shell diagrams is that 2 electrons are allowed in the first shell, and up to 8 are allowed in the next shell, 8 in the next shell, 8 in the next shell. So lithium only has 3, so 2 can go in the first shell, and then you have 1 remaining in the outer shell. Potassium, 2 in the first shell, 8 in the next shell, 8 in the next shell, and then just 1 remaining in the outer shell. So that's how they fill up. It's a bit like car parks. They fill up as you go through, and there's only allowed 2 electrons in the first shell and then 8 in the subsequent shells. Okay, next up is developing the model of the atom. Now, this is common content with the physics specification for paper 1, so I'd really recommend that you review this. Now, the whole idea in terms of developing the model of the atom is this statement here, that new experimental evidence may lead to a scientific model being changed or replaced. So I'm going to talk you through now how the model of the atom was developed and the evidence that we have for this. So early on, really early models of the atom described it as tiny spheres that cannot be divided. Later, the electron was discovered, and this led to the plum pudding model. And this is a model where it says the atom is a ball of positive charge with negative electrons embedded in it. Now, because of something called the alpha particle scattering experiment, the nucleus was discovered. And the nuclear model is the idea that the mass of an atom is concentrated at the centre and that the nucleus is charged. This was then developed by further scientists who then said that the electrons that are orbiting the nucleus do this at specific distances. And then later, someone said that protons and neutrons exist in the nucleus. So this is an overview of what's happened in terms of developing the model of the atom. Okay, next up is states of matter. So as you can see on the screen, we have got a diagram, particle diagram for a solid, a liquid and a gas. Again, common content with physics. Now, what you need to understand for your chemistry is that they might ask you about melting point and boiling point, and I'm going to show you 2 examples of that. So to begin with, melting point, this is the temperature at which a substance turns from a solid to a liquid. And boiling point is the temperature at which a substance turns from a liquid to a gas. So they could ask you a question, something like this, where you're given some information about some substances, some chemicals, and they are giving you there the melting point. And it says, what state is lithium at 100 degrees Celsius? So what you'd need to do is you'd need to look at that melting point and review your understanding of that. Understand that this is when it turns from a solid to a liquid. So what that means is that if there is a temperature below 180 degrees Celsius, it means it hasn't yet turned into a liquid. So the answer here would be a solid. You might be asked a question something like this, where they actually put it on a number line to try and help you with this. So here it says, what is the state of oxygen difluoride at minus 200 degrees Celsius? So you can see that the melting point is minus 224, the boiling point is minus 145, and that minus 200 would fit in between these. And therefore, if something has reached its melting point, but not yet reached its boiling point, we would say it is a liquid. It's not yet turned into a gas, but it's gone past its melting point and turned into a liquid. So for this one, it would be a liquid. Okay, so next up is about the structure and properties of ionic and covalent structures. We're going to start with ionic structures. Now here's an example of one and a diagram. This is sodium chloride, and within this we have got ionic bonding. So an ionic compound forms a giant structure of ions. And these ionic compounds are held together by strong electrostatic forces of attraction between oppositely charged ions. And these forces act in all directions in the lattice. This is called ionic bonding. So as we can see from this diagram, we have little positive ions. These would be your metal ions or your sodium ions. and we have the chloride ions. These would be our negative ions. And there are forces of attraction between these. We call these forces of attraction electrostatic forces. So if that's the structure, we're going to now link it to their properties and then try and explain why these things have certain properties. So firstly, ionic substances have high melting points and boiling points. And that means that large amounts of energy is needed to break the strong bonds. Large amounts of energy. They can also conduct electricity, but this is only when melted or dissolved in water. If it's dissolved, we call it aqueous. And that's because the ions are free to move and charge can flow. We've talked about ionic structures, and now we're thinking about covalent structures. So we need to understand that there are three examples here of giant covalent structures. We have graphite, the layers of graphite being called graphene. We have diamond, and we have silicon dioxide or silica. Now all of these have covalent bonds within them, and they are solids. So at room temperature we would find them as solids. Each of the atoms are linked by strong covalent bonds, and they have very high melting points. So that means lots of energy would be required to overcome those bonds and break them. Okay, let's start with diamond. We're going to look at diamond and its structure and its properties. Now, diamond is made of just carbon atoms, and these carbon atoms are covalently bonded together. Each carbon atom forms 4 covalent bonds. And we can talk about the properties as being very hard, having a very high melting point, and an inability to conduct electricity. Next up, we have graphite, or layers of graphene. Now this time, we have got carbon atoms, but each carbon atom forms 3 covalent bonds with 3 other carbon atoms. And this forms layers of hexagonal rings which have no covalent bonds between the layers. Now 1 electron from each carbon atom becomes delocalized. And so that means that it is able to conduct electricity. So graphite and diamond, both are made of carbon atoms, both have carbon atoms covalently bonded together, but the difference here is the number of bonds that they are able to form. Remember, diamond is able to form 4 carbon bonds, and in graphite there are just 3, which leaves 1 electron to be delocalized, which means it can conduct electricity. Okay, so another place where we would find covalent bonds are in small molecules. On the left-hand side are some examples of small molecules, and these are general formula that you should try and remember. H2O, water, CO2, carbon dioxide, O2, oxygen, Cl2, chlorine, and H2, hydrogen. Now, when we think about small molecules, we're thinking about pairs of electrons being shared. And these small molecules have low melting points and boiling points, and that means they're gases or liquids at room temperature. They don't conduct electricity, so they have no overall charge. Now, here's an example of a small molecule. This is water, or H2O, and this has a relatively low melting point and boiling point. And that means not very much energy is required to overcome these. Now, the reason this is not because of the covalent bonds that are within the structure. So these are actually really strong, these covalent bonds, but it's because between the molecules themselves, we have something called intermolecular forces. And these are really weak. And that means not very much energy is required to overcome these. And therefore, we can say that our small molecules have low melting points and boiling points. Okay, so I'm going to talk you through now how to do covalent bond diagrams for small molecules. Here are 5 examples of small molecules which have covalent bonds. Now, to do an electron diagram showing a sharing of electrons, we would need the periodic table to help us, and that will tell us how many electrons are in the outer shell of each of the atoms within the molecule. We're going to start with hydrogen. You will be given something like this in exam, which shows us the outer shells of our atoms. Now, in covalent bonding, the shells will be overlapping, and that's because the electrons get shared. So we're going to start with H2, hydrogen. Hydrogen is here on our periodic table, and it has 1 electron. Just 1. Now, remember, in our first shell, we are allowed up to 2. So actually, hydrogen will just need to have 1 more to claim to be an outer shell, full outer shell. So hydrogen, we're going to represent the hydrogen atom on the left having 1 electron with a cross, and the hydrogen on the right is going to have 1 electron with a dot. And they exist in the overlap, and now each atom can claim to have a full outer shell because it has 2 electrons in its outer shell by sharing with another hydrogen atom. Okay, next up we're going to look at Cl2. Cl2 is chlorine. Chlorine is found in group 7. The elements found in group 7, the halogens, will form pairs of atoms. So here we've got Cl2, but all of the ones in group 7 would be pairs. Now, because it's in group 7, it has 7 electrons in its outer shell. To have a full outer shell, it would need just 1 more electron. So we're going to represent our chlorine atoms electrons with crosses on the left-hand side here. So it's going to have 1, 2, 3, 4, 5, 6, and its 7th one is going to go in the overlap. The chlorine on the right-hand side has 1, 2, 3, 4, 5, 6, 7. So 7 electrons on that one too. Now the electrons in the middle there are the ones that get shared, and now each chlorine atom can claim to have a full outer shell. Okay. Oxygen. Oxygen is in group 6. Again, we have a pair of atoms. Oxygen has got 6 electrons in its outer shell. So to be a full outer shell, it would need to gain 2 more. So it's going to do some sharing of 2. So oxygen, we're going to represent the one on the left-hand side with crosses, is going to have 1, 2, 3, 4, and it's actually going to have 2 in the overlap now. 1, 2, 3, 4, 5, 6, with 2 in the overlap. Now, as you can see, each oxygen can now claim to have a full outer shell because it has 6 of its own electrons and then shares 2 with another oxygen atom. Okay, next up we have water, or H2O. As we discussed earlier, hydrogen has just 1 electron. To be a full outer shell, it would need to have 1 more. So we're going to represent our hydrogens as having these crosses, or dots I should have said, in the overlap. Oxygen is in group 6. That means it has 6 electrons in its outer shell, and it needs 2 more to have a full outer shell. We're going to get that from our hydrogens sharing those. So we're going to add some crosses to our overlap. So that's 2 of the 6 oxygen electrons. I'm going to add more like this. So now oxygen and the hydrogen atoms can all claim to have a full outer shell. And finally we have CO2, or carbon dioxide. Carbon is over here, it's in group 4, and that means it has 4 electrons in its outer shell. As discussed earlier, oxygen has 6 electrons in its outer shell. Now, carbon will need to have 4 more in order to be able to have a full outer shell, so it's going to need 2 from each oxygen atom. So that's where we'll start. Our oxygen we're going to represent with dots, so it's going to need to take 2 or share 2 electrons from each oxygen, so we'll start there. And we're going to represent carbon's electrons. Remember, it has 4. Now we're actually going to put 1 here, 1 here, 1 here, and 1 here. Now, if you looked at carbon, you can see that it has, or it can claim to have a full outer shell. And oxygen, remember, it has 6 electrons. We have done 2 here, so we need to do 1, 2, like this. And now it can claim to have a full outer shell. We can do exactly the same for this oxygen atom. Okay, jumping to neutralization now. Now, when we think about neutralization, we're thinking about this being between an acid and an alkali or a base. We're going to start by thinking about acids. Acids produce hydrogen ions in aqueous solutions. Remember, aqueous means dissolved. So here's an example, hydrochloric acid. When it's dissolved in solution, it forms hydrogen ions and chloride ions. And the hydrogen ions is what makes it an acid. Alkalis produce hydroxide ions in aqueous solutions. And these are represented by OH-. So here's an example, sodium hydroxide, which in solution will form sodium ions, Na+, and hydroxide ions, OH-. Now, during a neutralization reaction, the hydrogen ions react with the hydroxide ions and produce water. And this is why one of our products of a neutralization reaction is always water. So this is what it would look like, a hydrogen ion reacting with the hydroxide ion and forming water, or H2O. So in this case, if we were taking hydrochloric acid and we react it with sodium hydroxide, our product would be water. But we've also formed sodium chloride, and sodium chloride is an example of a salt. And this is our general formula for the reaction between an acid and an alkali, which is acid plus alkali arrow salt plus water. Okay, and finally we have endothermic and exothermic reaction profiles. So on the left-hand side, we can see a reaction profile for an exothermic reaction. This is a reaction where energy is lost to the surroundings. And this is because the reactants have more energy than the products. And this is seen on our diagram here. You can see the reactants have a higher line compared to our products. So there is some energy that is being lost to the surroundings. Now, this reaction profile includes this loopy section. And this loopy section is what we call the activation energy. This is the minimum amount of energy that's required for the reaction to take place. And you would measure the activation energy by looking at the difference of our reactants to the top of the loop. This is an exothermic reaction. An endothermic reaction is a reaction in which energy is absorbed from the surroundings. So this is going to look slightly different. We have our reactants showing that they have less energy than our products. And that's because energy gets absorbed and therefore our products will have more energy. Again, this will have an activation energy, which is the difference between our reactants and the top of our loop. This is the minimum amount of energy that's required for our reaction to occur. Okay, that is it from me in terms of walking you through some predicted content. There is a lot of things that I haven't been able to cover in this video, and this is where I would recommend looking at some other videos. So reactivity series, strong and weak acids, that's higher content only. Electrolysis require practical, the balancing equations and bond energy calculations. And if you are triple pupil, I would recommend looking at fuel cells. These links I will post for you so that you can link directly to those videos. These are from the Free Science Lessons YouTube channel, which I would highly recommend you look at. Okay, I hope that you have found the video useful and I wish you the best of luck.